Hello and welcome to the Metabolic Classroom. I am Professor Ben Bikman, biomedical scientist and professor of cell biology. Thank you for tuning in. Thanks for joining me during this discussion that we have today, where the episode topic is going to be energy toxicity. This is a topic that is a bit obscure. It's certainly not one that the average person would have not only any familiarity with, but certainly no appreciation for. So before we get started, I consider it quite helpful to do a little background here and even explain why this idea exists and what it hopes to explain. What it's attempting to provide an explanation for. So to answer that part of it, energy toxicity is an idea that is invoked to try to explain why a cell becomes insulin resistant. Now, this idea won't work for every cell. It's generally an idea that pertains to the cells that are capable of storing energy, primarily capable of storing energy as fats. And this is primarily now the liver and the muscle. So the general idea is that this condition, the idea behind energy toxicity, a certain metabolic state that's characterized by the accrual of excess energy. Now, excess energy can take a lot of forms. It can be glucose stored as glycogen, but this is primarily focused on triglycerides. And I already mentioned the tissues, that this is generally focused on muscle becoming insulin resistant because it's loaded with energy, but it also can be used. It's often also invoked with regards to the liver. But essentially, the idea being that as the cell becomes loaded with energy, it starts to become resistant to further energy storage. And a way to mount that resistance is to become resistant to insulin, because after all, insulin is the definite article there, the primary stimulus to tell a cell to store energy. There are other hormones that elicit an effect, but they all pale in comparison to what insulin does. Now, as much as I'm talking about energy toxicity here, there's another term for it. A synonym for this would be lipotoxicity. You might have heard that term before. If you haven't heard of any of them, lipotoxicity is perhaps a more accurate way of talking about this idea of energy toxicity, because after all, it's generally considered that the fat that is stored is the cause of the energy toxicity. That as much as a cell, is muscle and liver cell especially, is capable of storing glycogen, the evidence that glycogen storage promotes insulin resistance is very, very flimsy. Now, there are some lines of evidence that do support that, but primarily when people talk about energy toxicity, whether they know it or not, they're really talking about lipotoxicity. And to be clear, that's the idea that the excess storage of lipids are causing this toxicity, which itself is a bit of a strange term because it's not like the cell is infected with energy, but it's reached a point where the amount of energy is detrimental. And that's why people bring in the term toxicity here. So the lipotoxicity is a slightly more accurate version of the same thing, being energy toxicity. So to provide a little more background to this, this can apply to both glucose and fats. As we continue to talk about energy toxicity, that even when glucose is in abundance, it will primarily be stored in liver and muscles as glycogen. And then once the glycogen, traditionally, the way this will go is once the glycogen stores are met, any excess glucose, which there can be in excess quite readily, begins to be converted into fat, which muscle and liver do very well. And of course, fat cells do very well. Anyone who tells you otherwise is absolutely incorrect. A fat cell is perfectly capable of converting glucose into fat. Particularly, this changes based on the size of the fat cell, the particular distribution of whether it's the fat from the plasma from the blood that's contributing to the growth of the fat cell or whether it's glucose. It really depends on the size of the fat cell, but suffice it to say, glucose can contribute to the energy toxicity by nature of it being converted into stored fat. And then, of course, fat does this very well. Excess fat consumed with some important context, which we'll get to in a moment, will be stored. Now, this point is one that we will revisit because this is a fundamental concept of the energy toxicity idea, that this isn't necessarily fat that we're eating, but it's thought to be that we have fat that is coming from the fat cells. So fats that get stored as energy, stored as fat in the fat cells, then starts to come out of the fat cells and then getting stored downstream, if you will. Now it's getting stored in muscle and liver, leading to the lipotoxicity or the energy toxicity in those tissues, causing the insulin resistance. I'm going to state that again because it is a very important part of the energy toxicity model, this theoretical idea to explain insulin resistance, and it is one that we will revisit. So again, a lot of the idea behind energy toxicity is that you have too much energy getting stored as fat in tissues that are ill-suited for the long-term and excess storage of that fat, muscle and liver, and that much of that fat is coming from fat cells that are breaking down the fat. So the fat cell is undergoing lipolysis, the breakdown of the stored fat, and it is releasing these fats as free fatty acids, and then they're getting stored in other tissues. Another term for this is ectopic lipid deposition or ectopic fat storage. Ectopic being an idea where you're storing something where you shouldn't be, or something is happening where it shouldn't. Like you, for example, have heard, undoubtedly, you've heard the term ectopic pregnancy. That's when the pregnancy or the fetus is developing somewhere other than the uterus, maybe in a fallopian tube, or maybe the fertilized egg got out of the fallopian tube through some retrograde action and it's happening somewhere else in the abdomen. Or anyway, ectopic is when something's happening where it shouldn't be happening. And in the case of ectopic fat storage, it's when the fat is basically forcing other tissues to start storing fat. All right. Again, that's a fundamental concept of energy toxicity, and it's one we're going to revisit. Now, is it that simple? Is it just as simple as the fact or the idea that the muscle and the liver starts storing fat and then they become insulin resistant? No, it's not that simple. We need to firstly understand the role of triglycerides, and I'm primarily going to focus on the muscle because that is the heart, that is the tissue of interest primarily when it comes to energy toxicity. People will use the term energy toxicity to explain muscle insulin resistance primarily, but also liver, and some of these ideas still apply to the liver. But we're focusing mostly on muscle cells. So first of all, we have to understand how muscle cells store fat. Muscle cells naturally have a capacity to store fat. That's a very important point. That and it's the type of fat that matters most here. Actually, that's more important than the amount of fat the fat cell is storing, the type of fat. And speaking of types of fat, a cell, including a muscle cell, has the potential to contain thousands of different types of fats. Yes, thousands. When we talk about fats, this is a topic within biochemistry that is so massive that there are people who've devoted their entire careers to being lipid biologists. So there are thousands of different types of fats stored in every cell, muscle cell included. Now, which of them matters? Well, traditionally, whether people know it or not, when they talk about the fat that is getting stored in the muscle, they are talking about a type of fat, the family of which is called the glycerolipids. Glycerolipids are an important class. They represent among the greatest amount of fat that we store in cells. But the most common form of a glycerolipid is the most famous because it's the most abundant, triglycerides. This is what fits it into the family of a glycerolipid because as I'm acting it out with my hand here, along what would be my knuckles would be a molecule called glycerol, and that's where the glycero part of glycerolipid comes in. And then on a triglyceride, we have 3 fatty acid molecules coming off of the glycerol backbone. So triglyceride is the primary form of the glycerolipid, and the triglycerides are the primary form of fat storage in every tissue, every cell type that's storing fat. If it's storing fat to use for energy, it's triglyceride. Muscles, no exception. Neither is fat cells. When you look at a fat cell under a microscope, you literally have this big, for lack of a better word, a bubble or a ball of triglycerides all bundled up and squished together within the fat cell. Those are triglycerides. To a much more modest degree, what is a really big bubble of fat within a fat cell, you have small little bubbles of fat within muscle. That's a normal thing. The muscle is designed to have what is called intramyocellular lipids, or IMCLs. I'll just call it muscle fat. So triglycerides are stored in muscle cells as intramyocellular lipids, IMCL, or just muscle fat, which serves as an important energy reserve for the muscle, especially during exercise. So the muscle basically is smart enough, if you will, and pardon my unscientific description for a moment, to say there are times when I have substantial energetic needs, like when I'm exercising. And so rather than always have to rely on fat cells to give me fat, I'm just going to have a little bit of my own. I'm going to keep some in my pockets. And it is distinct. It's smaller little pockets of fat rather than a singular large bubble of fat like you see in a fat cell. Now, having said all of this, and you appreciating that fat cells naturally have more fat in them, what had been seen for years is that when you look at the muscle from obese, insulin-resistant, type 2 diabetic people, they have much more muscle fat than what you see in people who are lean and insulin sensitive and not diabetic. That led to this. That gave birth primarily to the idea of energy toxicity. Well, that the muscle from the obese, diabetic, insulin resistant people has way more triglycerides in them. Thus, this fat is causing the insulin resistance. However, in 2001, with Brett Goodpaster's group, he was, I think, a postdoc at the time, they found that if you do a muscle biopsy and measure the intramuscular lipid, or the IMCLs of a trained endurance athlete, they have just as much fat in their muscle as you see in an obese, sedentary, insulin-resistant type 2 diabetic. This led to what is referred to now as the athlete's paradox. How on earth, then, from their findings, could we say that triglycerides, that this primary method of storing fat in muscle, is a cause of insulin resistance? It totally blew the whole cause of insulin resistance. It blew the whole idea apart. Indeed, proving it false. So from this work, we can conclude with absolute certainty that energy toxicity cannot be explained by triglycerides. But this is, again, please understand, that is the fat that most people blame. When you're talking about ectopic fat deposition, anytime you hear anyone talk about that, whether they know it or not, they're talking about triglycerides. And this study proved their work, and it was a series of studies now, and many other groups have confirmed this. The athlete's paradox confirms that it cannot be a result, that the insulin resistance differences cannot be a result of the triglycerides. Because again, as much as you see very high levels of triglycerides in the muscle of obese, insulin-resistant people, you see just as high a level of muscle triglycerides in lean athletes who are exquisitely insulin sensitive. Something doesn't quite work here. And this is something that adapts. So you could take a lean, insulin-sensitive person, and they start engaging in a frequent endurance exercise routine, and give them a few months, and then measure their muscle triglycerides, and it's going to be as high. It's going to increase double, triple, quadruple, and yet they are not any more insulin-resistant than they were before. They're still exquisitely insulin-sensitive. So exercise, a natural adaptation to it, is to increase muscle fat storage, or what some would say ectopic fat storage. But it clearly is not contributing to a problem. Indeed, it's a beneficial adaptation. So if it's not fat, then, that is explaining this idea of energy toxicity, what is it? How does the idea still survive? Well, there's a lot of debate that that does happen. But if it's not fat, what is it? Well, it is fat, actually. There is fat that does cause insulin resistance. It's just not a fat that's often talked about. And I want to make you aware of it. So if we're going to invoke the term lipotoxicity, which is far more accurate than energy toxicity, then there are some lipids that matter. But let me riff on that for just a moment. A cell doesn't have an energetostat. It doesn't have like a thermostat like device or molecular machine that is capable of sensing how much calories it has stored in it. I mean, well, a calorie is almost silly to invoke here because that's a unit of that's a thermal unit or a unit of measuring heat. The cell doesn't have a way of knowing how much chemical energy that it has stored in it as nutrients. So the whole idea of energy toxicity, to me, I find quite amusing. I think it's quite silly. Lipotoxicity, however, I think has some relevance to it, but it's not because of a certain amount of energy that these lipids contain, because in fact, the lipids that I'm going to mention don't directly contribute to energy. Well, one kind of does, the other doesn't. So what are the two lipid intermediates that are capable of causing insulin resistance? And as a reminder, there are thousands of different types of lipids. One is diacylglycerol or DAGs, and there's something familiar in that term, diacylglycerol or diglycerides, and then ceramides. Ceramides are the other one that we'll spend a little more time talking about for reasons that will become obvious as I explain them. So firstly, let's start with DAGs or diacylglycerols or diglycerides. You can sense in there, you can hear the triglyceride, and appropriately so. A DAG is a triglyceride that has lost one of its fats. You still have the glycerol backbone, but now you have only two fatty acids. The idea behind DAGs is that they may represent a process of lipolysis that's kind of gotten stopped, that you've taken a triglyceride molecule and then the muscle cell, for example, has started to break it apart to burn it, but there's just so much there that it can't get through the full process of pulling all of the fatty acids off. That is called lipolysis, to burn them, that it sort of gets stopped halfway. And this is a way of signaling to the cell that we're loaded with fat. The general pathway, as elaborated by Dr. Jerry Schulman, is that DAGs, when they accumulate, will activate a family of an enzyme in the cell called protein kinase C. And there's all different types of this, protein kinase C. Then protein kinase C as a kinase, and pardon me for we're getting a little molecular here, but a kinase will generally phosphorylate something else. It adds a little phosphate molecule. And basically in the process, it ends up disrupting the insulin cascade. So insulin comes and binds to its receptor. Then there's a series of essentially phosphorylation events, one thing phosphorylating another. And then when DAGs come in, they disrupt that. They basically disrupt the signal, ultimately causing insulin resistance. So that's it that I'll say about diacylglycerols as a type, as a lipid that could explain lipotoxicity, if not necessarily energy toxicity, although that one comes the closest of combining those ideas. Now, ceramides, in contrast, are part of a family, whereas diacylglycerols are part of the glycerolipid family. Ceramides are part of the sphingolipid family, named after the enigmatic Sphinx, because for so long, people didn't know what sphingolipids did. And their original role was thought to be nothing more than, although not to say it's not important, causing apoptosis. So ceramides were originally considered to be simply a cause of signaling cell death. Now, however, we know and have for the past several decades that they do much, much more than that, including causing insulin resistance. In particular, ceramides inhibit a different signal in the insulin pathway. So it's a little further down. And that I won't get into the specifics, but again, ceramides will interact a little further down. Ceramides as a molecule also influence mitochondrial function. So a lot of this work that I'm mentioning is from one of, in fact, he's a very good friend and a mentor to me, literally a mentor. I did my postdoctoral fellowship with his work, and I invite anyone to look up his work. His name is Scott Summers. So a lot of this has come from the lab of Scott Summers, but confirmed in labs across the world, including a lot in Europe and throughout the US, but indeed worldwide. So other work, including some from my own lab. You can look up the work of Smith et al. She was my PhD student, 2013. We found that ceramides also disrupt mitochondrial dynamics, that when ceramides go up, part of how they may be causing insulin resistance, in addition to disrupting the phosphorylation cascade, similar to what DAG does, but in a different spot, we found that ceramides also force mitochondrial fission, which it increases the production of reactive oxygen species, and that change results in a redox sensitive change in other enzymes. So it's basically an additional mechanism that explains how ceramides could be causing insulin resistance, fitting into the lipotoxicity idea. However, ceramides cannot be burned as a fuel. They don't provide any caloric energy to a cell, any potential to create ATP. So now we've uncoupled the lipotoxicity from the energy toxicity idea, whereas DAG attempts to keep them together. Ceramides pull them apart. Now, I have no problem confessing between these two mediators, it's very possible, and there's good evidence to support both. It's possible they both contribute. I have a very heavy bias in favor of ceramides because I've literally done the work with my own hands. And the work from my old lab, in 2003, you could look up the work by Chavez et al. The name of that article in particular is called A Role for Ceramide, but Not Diacylglycerol in the Antagonism of Insulin Signal Transduction by Saturated Fatty Acids. So what they found here is that something I've talked about before, so please look up my previous Metabolic Classroom talking about saturated fats. Saturated fats at a level of a cell, which again is not the same as eating saturated fat, because after all, most saturated fats in the blood come from the liver making it. And what stimulates the liver to make saturated fatty acids? Insulin. But nevertheless, saturated fats are capable of causing insulin resistance. And what this study found, what they found, Chavez et al. In 2003, was that you could block the DAGs and the cells would still become insulin resistant. You could allow the DAGs to form, but if you blocked the ceramides, the cells would not become insulin resistant. So one of these was necessary for the insulin resistance. One of them was not. All right, so when are ceramides a problem then? As we continue to unpack the energy toxicity, and generally, I want you to appreciate that I'm challenging the idea of energy toxicity. I don't think that's a valid idea. I don't think it's a valid explanation for insulin resistance. Lipotoxicity is another matter, but it's not because of the energy or the caloric value of the lipid. It's because of the direct interaction of the lipid with the insulin cascade. So among the lipids that I deem the most relevant with the lipotoxicity in mind stands ceramides. They stand apart. Again, I'm biased. I have literally published this work and focused on ceramides throughout both my dissertation work, my postdoctoral work, and including being an independent investigator managing my own lab. So when are ceramides a problem? When would lipotoxicity then be something that we need to consider? Well, it won't surprise you when I explain these three primary causes of ceramides, because they're the primary causes that I've discussed in previous Metabolic Classroom episodes as the primary causes of insulin resistance. Chronically elevated insulin will increase ceramide accumulation, which then causes insulin resistance. This was a paper we published from my lab a few years ago. Inflammation will cause insulin resistance, whether that inflammation is from saturated fats, whether it is from inflammatory proteins that are coming from overfilled fat cells, or whether it is bacterial remnants coming from the leaky gut, like a bacterial remnant called lipopolysaccharide, or LPS. That was the primary focus of my entire fellowship. So in fact, my highest impact factor article I've ever published was that work, detailing the pathway of how LPS, this bacterial remnant that can come in from the gut through leaky gut, can cause insulin resistance. So inflammation is another primary cause, and then stress. The stress hormones like cortisol will cause insulin resistance, but if you block the ceramide in every one of these, incubate a cell with high insulin, it becomes insulin resistant. But if you block the ceramides, they don't. If you incubate the cell with pro-inflammatory mediators, increase inflammation in the cell, then it will become insulin resistant. But if you block the ceramides, it maintains some insulin sensitivity. Now, lastly, incubate a cell with cortisol, the primary stress hormone, if you will, it will become insulin resistant. Block the ceramides, it won't. So you can see why it's something I point my finger at so readily. It's because it just fits. The every line of evidence continues to support this idea. Now let's start to, as we near the end of this lesson, talking about energy toxicity. And again, you hopefully getting what I'm clearly stating, which is I don't think that idea itself holds a lot of value, but there's some nuance there. So let's go to another level of nuance. Let's revisit the concept that I mentioned earlier, this idea that the lipotoxicity is a result of lipids that are coming from a fat cell and then getting stored somewhere else. The ectopic lipid or the ectopic fat storage idea, that as the fat cell can't store any more fat, then other tissues like muscle and liver are left to pick up the slack, metabolically speaking. Well, let's just talk about the physiology or the biology of the fat cell for a moment then. When would a fat cell be experiencing lipolysis? And remember, lipolysis is the term for taking a triglyceride molecule and pulling off the fatty acids, which are then released from the fat cell as free fatty acids. And then the idea with ectopic fat storage is that other cells are then pulling in those fatty acids and storing them. They're basically it's called a process of re-esterification, where you have a glycerol backbone, and now it takes a fatty acid, in this case coming from the fat cell in a muscle cell, and boom, adds a fatty acid, giving us a monoglycerol. Then boom, another one, giving us the diacylglycerol, the diglyceride that we talked about earlier, DAG. And then another one, boom, and we have a full-on triglyceride that we're storing. Well, when would this be happening? When would the fat cell be breaking down its fat? Well, the most common, most obvious instance would be when insulin is low. That's very, very important. When insulin is low, lipolysis is disinhibited. In other words, the fat cell can now suddenly start breaking down as much fat as it wants to. So that would be an instance when the fat cell is breaking down its fat, sharing it with the body, and then getting pulled into cells, which it would do very readily. A muscle cell is happily going to pull in those fatty acids. Why do I say happily? Why am I using that particular adverb? Because insulin is low. And because insulin is low, the fat cell will know what to do with it, which is burn it. What about the liver? The liver will look at that free fatty acid, and happily take it in, because if insulin is low, it will burn it. In fact, this is what's happening during a fast or during a ketogenic diet. It is ketogenic at the liver because the liver can't stop burning fat. Why? Because insulin is low. If insulin is low, the liver keeps getting all these fatty acids from the fat cell, and rather far from storing it, creating an ectopic fat storage problem causing fatty liver disease, the liver just keeps burning it. And in fact, is burning it so much, these fats, that it starts creating ketones from the burning fat. Ketones essentially is the liver cells saying, I'm burning as much nutrients as I need to meet my needs. I'm filled with energy now, but I can't stop burning fat because insulin is low. And so now I'm going to keep burning it, but all the rest I'm going to convert into ketone. So it's essentially the excess kind of pressure valve, where the liver cell has a way, an outlet, to continue to burn fat, even though it doesn't need the energy from the fat. It doesn't need the ATP from the fat burning anymore. So it converts it into ketones, saying there are other cells throughout the body that can now use it, like the brain, as an example. But indeed, any cell with mitochondria will burn ketones. So that's what happens then. If insulin is low, lipolysis is now active at the fat cell. And in this state, the body will not store any of that energy. Whether it's the muscle pulling it in, the liver pulling it in, or any other cell, it's going to burn it. Because in the presence of low insulin, it's allowed to, and indeed it's encouraged to. It has no option but doing that. Now, however, what if we had a scenario? So in fact, before I move on, let me just compare this then. So if you have high free fatty acids in the blood in a normal situation, that is happening because insulin is low. In other words, a fasted or a low carb diet, fasted state or low carb diet. Low carb diet, I call a ketogenic diet a nutritional fast or a nutrient fast, because it maintains the same kind of biochemistry of a fasted state, namely low insulin, high ketogenesis. In contrast, in the fed state, when you've eaten a mixed meal, like with carbs, Then all of a sudden the insulin is high, and the high insulin inhibits lipolysis. So no surprise that free fatty acids go down. The body is more interested in storing energy rather than breaking it down. And that is reflected by a reduction, among other things, in free fatty acids. Now, imagine, if you will, a scenario where both of them were elevated. Now we're cooking with gas. Now we are talking about lipotoxicity, and basically the body is filled with energy and it can only store it. So I don't even mind if someone wants to invoke the idea of energy toxicity here, as much as I disagree with it in principle. When could that happen? I just explained that these two are inversely related. High insulin is low free fatty acids. Low insulin is high free fatty acids. When would they ever both be elevated? Where insulin is high, but it's clearly not capable of inhibiting the lipolysis from the fat cells. Thus, free fatty acids are also elevated. Well, clearly the insulin isn't working. The fat cell isn't listening. It has become deaf. Insulin is screaming at the fat cell to inhibit lipolysis, but the fat cell, having become insulin resistant, no longer gets the message and is now breaking down the triglycerides, one free fatty acid at a time, releasing it into the blood. Now, in the presence of high insulin, when the muscle pulls in that free fatty acid, it thinks, yeah, I would have loved to burn you, but I can't. Insulin is forcing me to store it. And indeed, that's what happens. So now the muscle is storing fat and accumulating triglycerides. But now let's go to the liver. The liver, the same thing. The liver would say, look, once upon a time I was burning you and making a lot of ketones from you, but because insulin is high, I can't. I have to convert you into triglycerides and start making my own big bubbles of fat, creating fatty liver disease. So here we have a very different scenario. Even though the free fatty acids are still elevated like they were before, when insulin is also high, now we have ectopic fat storage. But is it the fat that's causing the insulin resistance? No, it's not. Because remember, the triglycerides are also high in the athlete's paradox scenario. So if we have high fat storage in an athlete and it's not causing insulin resistance at all, it can't be the fat storage that's the problem. So to kind of wrap all of this up, what is different then from the obese insulin resistant person who has high muscle fat levels and the lean insulin sensitive athlete who has high muscle fat levels? It's clearly not the fat. They may both, in fact, have high free fatty acids because they're both undergoing lipolysis. But unlike the lean athlete who's experiencing lipolysis because his or her insulin levels are low, the obese insulin resistant type 2 diabetic has high insulin, but they're insulin resistant. So it cannot be the fat storage that's causing the problem when we talk about energy toxicity as a cause of insulin resistance. So is energy only toxic when the insulin is high? Yes. Yes, it appears that it is. But then the simpler explanation is that then it's just high insulin that's causing the problem. Because when insulin is high, you can't burn the energy. You have to store it. But it's not the energy itself. It's not the stored energetic molecules that are causing the insulin resistance. It's a signal from the high insulin. This is why I so often can come back that if you're going to try to understand insulin resistance, among the myriad causes, and there are more than just one, focus on the high insulin. High insulin is the most common cause, chronically elevated insulin, to be precise. When insulin is chronically up, that's the primary cause of insulin resistance. Now, some people want to misunderstand what I'm saying. I'm not declaring war on a singular insulin spike, but that is increasingly uncommon. Even in an insulin-sensitive person, someone eats a starchy, sugary meal, insulin is up and down, and it takes about 2 to 3 hours before the insulin comes back down. This is in a healthy insulin-sensitive person. If you take an insulin-resistant person, which is the majority of adults worldwide now, then that what was a 2 to 3 hour insulin spike becomes a 4 to 5 hour insulin spike. Well, before the insulin ever has time to come down, they've bumped it back up again. Especially because we have, after our starchy, sugary breakfast, we have a starchy, sugary mid-morning snack. And then we have a starchy, sugary lunch. Then we have a starchy, sugary afternoon snack and dinner and evening snack. And so a person is spending every waking moment and even several hours into their sleeping moments with elevated insulin. So we cannot pretend that chronically elevated insulin is uncommon. Indeed, I would suggest strongly, I would submit that it is the more common scenario nowadays. Also, keep in mind that the dose matters tremendously. There was a study published years ago that found that even lean, healthy, college-aged males who are very insulin sensitive, if they eat a few 100 grams of carbs, their insulin was elevated for up to 10 hours. We all know how easy that can be to eat a few 100 grams of carbs. It's not hard. And again, even in them, their insulin was elevated for almost half of a day. So energy toxicity, lipotoxicity, I think if we were to even break it down to a simpler and more precise understanding, we could say that it's insulin toxicity. Too much insulin causes insulin resistance. And there are lipid intermediates that actually connect it, the high insulin to the insulin resistance. And I believe that primarily that involves ceramides. All right. I hope you feel like you've learned something new. These are deep ideas. The ideas of energy toxicity require some deeper understanding, undoubtedly. I hope I've been able to explain it in a way that's let you follow along. Remember, all of it is just an effort to explain what is now the most common singular health problem worldwide, namely insulin resistance. Thanks again for joining me. Until next time, more knowledge, better health.